Alaikum. Today's lecture we are going to continue talking about the wind energy. In this section, we are going to talk about the wind farms. Wind farms is very important to study because a single wind turbine is going to provide you with a certain electricity. But if you want to increase the amount of electricity generated, you need to install wind farm. So most often when a good wind site has been found, it makes sense to install a large number of wind turbines in what is often called wind farm or wind plant. So the question is whether there are sufficient wind resources to supply a significant fraction of electricity demand, whether the land areas required to do so might be excessive. To answer those two questions, we have to go to the NREL. NREL, it's an abbreviation, stands for National Renewable Energy Laboratory. NREL began developing maps of the United States wind resources back in the 1980s. With these maps as a starting point, NREL has attempted to estimate the nation's total wind potential on lands outside of wilderness area, parks, urban areas, and other regions unlikely to be developed. So this is one example of the NREL developed maps for the United States wind resources, and they classified the wind potential areas in different classes: class 1, class 2, class 3. Here another area with class 2, class 3. Here is class 4, class 5, and class 6, and so on. So in this side, we are going to talk about the capacity factor, CF. Capacity factor definition is a convenient dimensionless quantity between 0 and 1 that connects rated power to energy delivered. So the fraction of the year the turbine generator is operating at a rated peak power is CF. Capacity factor can we write it down as average output divided by peak output, or actual energy delivered divided by 8,760 hours per year over the rated power PR. So the average power divided by the rated power, this is CF. CF is based on both characteristics of the turbine and the site characteristics. So typically it's almost 30% in most cases, 0.3 or above for good site. This is one example how to apply the CF. What is the capacity factor for the NIG Mekon 1000 over 60 with actual energy delivered of 2.851 times 10 to the power 6 kilowatt hour per year and rated power of 1000 kilowatt? So how to calculate CF using this formula? So CF is the annual or the actual energy delivered, which is 2.851 times 10 to the power 6 kilowatt hour per year, divided by 88,760 divided by PR, which is the power, the rated power. Rated power here in this example is 1000 kilowatt. So kilowatt hour per year goes with kilowatt, and here is hour per year. So you end up with 0.325. So this is the capacity factor of this wind turbine. So it's straightforward to calculate it. Another example, let's see how to solve this example. Compare the current 4 billion megawatt hour of the United States electricity demand with the total onshore wind potential at 80 meter for the turbines having 35% CF, and again for 100 meter turbines with 40% CF. Assume 10% rotor wake losses between turbines. So we have two different types of turbines. The first one is 80 meter, 35% CF, and the other type of turbines 100 meter diameter with 40% CF. And the amount of electricity generated 4 billion megawatt hour. So how to compare between them? We are going to use the same formula. CF equals actual energy delivered divided by 8760 times PR, the rated power. So it's known the CF for each turbine, and it's known also the rated power. So here is the graph. In this graph, this shows the onshore potential gigawatts, the rated capacity over indicated CF in gigawatts versus the gross capacity factor for each turbine. So for 80 meter, this curve, and for 100 meter, this curve. For 80 meter at 35% capacity factor, it will give you 8,000 rated capacity, 8,000 gigawatt. While at 100 meter hub height turbine working at 40 CF, it will give you 7,500, almost 7,500 gigawatt. So from the figure, let's start with the 80 meter height wind turbine. This type of turbine can provide you with the 8,000 gigawatt of power at 35% CF. So including the wake losses, that works out to, what is the available power? It's CF multiplied by 8,760 times the rated power, which is 8,000 gigawatt, multiplied by 1 minus the losses, which is 10%, so you multiply by 90% or 0.9. So 0.9 times this will give you 22.1 times 10 to the power 9 megawatt hour per year. So this is more than 5 times as much electricity as is now being used. If we go back to the example, so the current use is 4 billion megawatt hour. And what you are going to get is not 4 billion, but we are getting 22 billion. So it's almost 5 times as much electricity as it is now being used. For the other type of turbine, 100 meter, so it produces the rated power of 7,500 gigawatt at CF 40%. So we are going to apply the same formula, 0.4 times 8,760 times 7,500 gigawatt times 90%. Will give you 23.6 times 10 to the power 9 megawatt hour per year. So this is almost 6 times the total electricity is being used today. This example, we need to estimate the permanently distributed area of land needed to provide half of 4 billion of megawatt hour per year of the United States electricity demand. Assume the turbines are located in the sites with the 7.5 meter per second average wind speed. Assume NERL's permanent direct use area of 0.74 acres per megawatt. So in this example, you need to calculate the total amount of the energy delivered. So we are going to use this formula. So we need to know CF and PR. How to calculate CF from this formula? CF equals 0.0435 times the average speed. So if you know the average wind speed, you can calculate the CF Once you know CF and the rated power, you can calculate the actual energy delivered. Okay, so CF, when the average unit speed is given 7.5, so 7.5 times this, will give you 0.326 CF. Once we know CF, we can calculate the rated power. Here, the unknown is the rated power because the total energy delivered is given, half for billion. So we need to calculate the rated power. So PR is half for billion divided by 8,760 times CF, which is 0.326. You get 0.7 times 10 to the power 6 megawatt. So this is the amount of the rated power. Once we know the amount of the rated power, it's given that the area 0.74 acres per megawatt. And we know the rated power of total number of megawatts. So we'll multiply this by the given rate, 0.74 multiplied by the total number of megawatts. It will give you the total number of acres. This is the area. We can convert it to miles square or square miles or kilometer squares. So it will be 2,100 kilometer squares. So this area is less than 0.2% of the 300 million AC of the co-plant harvested each year in the United States. And if we look into this area, it's the small black square here. This will provide you with the half of the United States electricity demand. But when you install the wind farm in this area, you will use this big square, which is the array area, and use the buffer zone, which is this area. So this small square will provide the United States with half of its electricity demand. Towers for a flat terrain. We install the wind farm like this. This is the wind turbine. Between this, we are going to make a row. And this row consists of the spacing, or the diameter of the wind turbine is D. So the area will be 5D times 10D. So the spacing between each turbine will be 5 times the diameter, 5D. And we are going to install one row. The spacing between each turbine is 5D. And between one row and the other row, you have to keep the distance 10D, 10 times the diameters. So this is why in this way, you are going to form a wind farm. This is another example for an array. So suppose that this is a wind turbine. You have to keep a distance 5D between one turbine and the other along the row. And between one row and the other, you have to keep distance 10D as we mentioned. And we are installing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 turbines each row. Times 3 columns, 10 times 3, 30. We have 30 turbines. So what will be the total area? Here is 10D and 10D, so this is 20D. This is 5D and 5D times 9, so 9 times 5D, 45D. So this is 45D and this is 20D. You have to keep buffer zone, buffer area, 10D from here, 10D from here, 10D from here. So the total area will be 45D times 20D. This is for this area. And you have to add 10 plus 10, so it becomes 20 plus 20, 40D, and 45 plus 10 and 10, 65D. So the total area becomes 65D times 40D with buffer. Okay, let's take an example. estimate the array area required for the wind farm consisting of 30 turbines. Each turbine delivers 2 megawatt rated power with a 90-meter diameter. In 3 rows, 10 turbines each with using a 5D times 10D tower spacing. Then add an additional 10D of buffer space around the entire turbine array and find the total area required. Also find the power density ratio. So we are going to use the scheme we studied before. So the area becomes, as we mentioned before, the area becomes 9 times 5, 45D, times 2 times 10, 20D. So 45D times 20D, it gives you 900D squared. And we know that D equals 90, so 900 times 90 squared will give you this area in meter squared, square meter. This is the area without buffer zone. After adding, before calculating the total area with buffer zone, we need to calculate the power density ratio. So power density ratio will be the rated power, which is 30 times 2, it will give you 60 megawatt for the total wind farm. 60 megawatt divided by the area, it will give you the power density ratio. So the power density is 21.3 megawatt per square mile. Because here we are going to convert from square meter to square mile, or you can keep it megawatt per square meter, no problem. Suppose that this is the power density here. After adding the buffer zone, the area will not be 45 by 20D squared, it will become 65 by 40D squared, as we mentioned. So here we need to add 20D and 20D here, so it becomes 65D times 40D. It will give you 2600D squared. And D is 90, so it will end up with 21 times 10 to the power 6 square meter. So when you divide the same power by the area, the new area will end up with new power density, which is 2.9 per kilometer squared, or per mile squared 7.4. It was 21.3. So there is a drop after using the buffer zone. So you increase the area, but the amount of the electricity is the same, fixed. So you end up with the smaller amount of power density. This is expected. In this section, we're going to talk about the offshore energy. So in the previous section, we talked about the onshore wind farm, but here we are going to talk about the offshore in the sea. So this is one example of the offshore wind farm installed in the ocean. The offshore wind farm, while onshore wind farms have been the dominant source of wind power globally, the now small but rapidly growing offshore market has considerable potential for the future. Advantages for offshore wind farm, and these advantages are stated below. So the advantages of offshore wind farm tends to be stronger, steadier, and less turbulent, and they frequently flow in the afternoon when the power is most valuable. The advantage is the marine environment is harsh, access for maintenance purposes can be difficult, and costs are considerably higher than land-based installation. So this graph shows the cumulative wind generation capacity, the cumulative installed capacity in gigawatt versus the years. So there is a great interest with the offshore wind farm compared to the land-based or onshore, and there is especially currently and for the future. Offshore wind energy technologies, there is different types. This is onshore. This is offshore, but for shallow water, less than 30 meter deep. It's called monopile. And there is, if the water is going deeper, it's called transitional water from 30 to 60 meter depth. Its type is jacket structure. Here, the installation here. And if you go deeper and deeper, greater than 60 meter, so this structure called floating platform. For cases of small systems close to the shore, may run multiple undersea AC cables from strings of turbines to shore. Like here, this is offshore radials. They are using multiple undersea 33 kilovolt AC cables here, and they are connected together to the onshore AC station and then to the grid. This is for small system less than 30 kilometer in length and less than 100 megawatt in electricity. For larger systems, less than 90 megawatt or from 100 to 500 megawatt, they are going to install 33 kilovolt AC cables, then 33 to 132 kilovolt transformer, offshore transformers to boost the voltage before transmission to the shore. Then there is offshore 132 kV cables until you reach to the onshore cables and then go to the AC substation. This is an example of submarine cable, cutaway view of a 132 kilovolt submarine cable. Transmission from the offshore transformer to substations on the onshore is provided by three-phase submarine cables. Since the individual conductors in these cables are so close together, they have much more inherent shunt capacitance than typical overhead lines onshore. While overhead lines are inherently inductive and hence absorb reactive power, three-phase submarines cable creates reactive power VARs. For larger systems located farther offshore, for example, that's generating from 200 to 1000 megawatt, high voltage DC transmission become a variable and in some circumstances necessary option. Like you are going to use 30 kV AC and here 30 kV AC, and this you are going to use 132 kV AC until you reach to the offshore and you convert from AC to DC and you transmit it with the high voltage DC cable with the length 40 to 300 kilometer until you reach to the offshore. You convert from DC to AC converter and then you go to reach to the AC substation. United States offshore wind resources actually from 0 to 30 meter, less than 30 meter is here. From 30 to 60 here, above 60 is here in this area. And it's in this map, you are going to see the region with the energy resources in gigawatt and the total energy resources with these types. This is an example of Atlantic wind connection transmission backbone starting from Virginia, passing through the Maryland, Delaware, New Jersey, and they are connecting these together to get the benefit of the offshore wind turbines. An example 5 are going to see how to apply this information. Using the neural assumptions of 5 megawatt turbine placed on uh, on every square kilometer of water with an annual average wind speed of above 7 meters per second. Estimate the area and the energy generation potential in water less than 30 meters deep. So we have this turbine offshore producing 5 megawatt with average wind speed 7, and we need to calculate the area and the energy potential for this type of turbine. It's called monopile, installed in the shallow water with the depths less than 30 meters. So based on the data given by the neural for the turbine installed less than in shallow water less than 30 meters deep, you have to get this information. So based on this information, we are going to use these formulas. Based on the given wind speed, we can calculate CF. Based on CF, we can find the actual energy delivered if we know the rated power from this. Okay, so here CF is this times 7, you get this number. Annual energy generation, this CF multiplied by 8,760 times the rated power. The rated power from here, we get it from this table. Rated power 1071.2 gigawatt. So once we know the rated power, the CF, we get the annual generation gigawatt hour per year. And this is one of the requirements, the energy generation per year. Then we need to calculate the area. So once we found we have a turbine that's producing 5 megawatt, and we need the power generated, or the rated power is 1071, so divide 1071 by 5 megawatt, you get the number of turbines needed. So the number of turbines need almost 214,000 turbines to produce this amount of rated power. Then one turbine per square kilometer, they would span an area of about, because it's given in the example here that this turbine is placed on every square kilometer of water. So once you know the number of turbines, you know the area in square kilometer. So the amount of the turbines becomes the same of the area in kilometer square. So it will be 2014 or 214,000 kilometer square. And we know that the annual energy generation or energy production is almost 2.86 million gigawatt hour per year, and the current total generation in the United States is almost 4 million. So that the shallow water resource could be sufficient for more than half of the total. This is the end of our presentation today. Thank you for your attention.